Theoretically speaking, anything could become a black hole. You, me, this pen, everything has what is known as a Schwarzschild radius. If you collapsed all the matter of an object into an area defined by the Schwarzschild radius, the density would be so great that the gravitational pull would be so great that nothing, not even light, would be able to escape its pull. The Schwarzschild radius for, say, the Earth would be the size of a peanut. What this means is that if you took all of Earth's matter and compress it into something the size of a peanut, you would have a black hole. Luckily, there's no known way to compress anything into such a small space. However, a star, many times the size of our own sun, has a much larger Schwarzschild radius. A star has two forces acting on it. Firstly, the inward force of gravity, and secondly, the outward force from the reactions occurring inside the core of a star. When a fuel of a star runs out, there's no more outward force and gravity takes over. The star starts collapsing in on itself until it reaches a single point of infinite density called a singularity. If further pressure is applied onto the core of a star, a powerful shock wave can be sent out, which literally blows the star to shreds. If further pressure is applied, the star's core can be crushed down to an ultra-dense object called a neutron star. If further pressure is applied, the neutron star can literally be crushed down to nothing. When this happens, a black hole is formed. The matter which collapsed in to form the black hole is gone, however, it leaves behind a strong and powerful legacy. It's gravity. The point of singularity is surrounded by a black sphere called the event horizon. This is the point of no return. Anything which crosses the event horizon cannot come back and is gone forever. This is because of the strong gravitational pull of a black hole. Everything that has mass or energy is affected by gravity. Everything that we know of in the universe has either mass or energy. A black hole cannot be seen directly, but its presence can be determined by the effect it has on its surroundings. A black hole's strong gravitational pull warps space and time around it. Anything which is behind a black hole, according to the observer's position, appears warped and deformed. This is called gravitational lensing. Gravitational lensing is different from optical lens. In gravitational lensing, there is a focal line rather than a focal point, and in gravitational lensing, maximum bending of light occurs closest to the center with minimum bending occurring furthest away. If the observer, lensing object and the light source are in a straight line, the light source would appear as a ring around the lensing object. This is referred to as Einstein's ring. In most cases, the forward momentum of two black holes causes them to orbit each other. They keep spinning around each other until one swallows the other and grows in size. When two black holes orbit each other, they speed up and disrupt the otherwise smooth fabric of space-time, like ripples formed when a pebble is tossed into a body of water. Similarly, the collision of two black holes sends out large gravity waves. These waves carry with themselves energy away from the black holes. This further draws the two black holes closer together. A black hole spins faster towards the center and slower further away. This causes the gas and stars to flow into the black hole in a rapidly spinning disk. This spinning motion produces magnetic fields which twist around. These fields channel the inflowing matter into a couple of high-energy jets. This causes the two jets seen on either side of a black hole. The energy produced here is much greater than all the energy that can be obtained from the fuels inside a star. If a black hole is about 2 to 3 solar masses, its gravitational pull rises sharply. If anything, say a starship, went near such a black hole, the head of the starship would experience a much greater effect of gravity than the tail. The starship would effectively get ripped to shreds. In contrast, however, your ride into a supermassive black hole would be much smoother, as the gravity will be more spread out over a larger surface area. No one knows for sure what happens when something crosses the event horizon. However, some scientists, keeping Einstein's equations in mind, believe that it is similar to traveling down a river and then falling down a waterfall. A spinning black hole is thought to have an inner boundary called the inner horizon. When an object enters a black hole, it accelerates to up to the speed of light. It rotates around the inner horizon at such great speeds that it might just get flung outwards and out of the black hole. This would be like a river running down a waterfall, hitting the rocks below and then flowing back up. Basically, it would enter a black hole, speed up, and leave it. As you cross the event horizon, you would be able to see the outside world, but the outside world would be unable to see you. This is because light cannot escape a black hole. As you approach the central zone, you would start moving around the inner horizon and speed up until you would be hurled through a cosmic tunnel known as a wormhole. You would exit through a white hole and reach another time, place, or maybe even another universe. This, however, is only in theory. In practicality, this would be near impossible, as objects falling into a black hole would collide with objects coming out, and there would be utter chaos. In a waterfall, this would be the part where the water flowing down collides with the water flowing back up. On Earth, much of the energy released by gravity quickly dissipates, and objects that fall to the ground settle into a state of rest. This, however, is not the case in black holes. In black holes, the energy builds up on itself until it reaches an extreme point called the Planck density. The Planck density is approximately 10 to the power 93 grams per centimeter cube. Think of this as taking all the matter in the observable universe and crushing it all down to less than the size of an atom. Temperatures here rise to trillions of times hotter than the core of our own sun. If this energy is released, it would have destructive effects on the universe. Luckily though, the gravity keeps it within the boundaries of a black hole. At this point in time, much of the energy in the universe is produced by stars burning their fuel. It is expected that in a few trillion years, the stars will use up their fuel and fade away. They will form neutron stars, white dwarfs, and black holes. Then further on into the future, the black holes will merge together and form larger black holes. Eventually, all the matter in the universe will fall into these black holes. At this point, the black holes would be the only beings surviving in the universe. But would they last forever? A theory suggested by Stephen Hawking might just give us the answer. The theory predicts that the black holes would not be black but would glow with heat radiation. But this heat radiation would have to come from somewhere. Hawking says that this radiation and energy comes from tiny particles emerging from the vacuum of space just outside the event horizon. These particles move away and take with themselves small amounts of mass from the black hole. Over time, this radiation increases, and the black hole shrinks until it explodes. According to this theory, when a large black hole explodes, that could be the end of the universe as we know it. Radio astronomers have searched for electromagnetic pulses associated with the disintegration of black holes, but up till now have not found any. But there might be other ways to see a black hole decay. Black hole jets are blasting out particles at near the speed of light. These particles are called cosmic rays. They may enter our Earth's atmosphere with enough energy to form miniature black holes. These decay almost immediately and are very difficult to explore and observe. The Brooklyn National Laboratory in New York is thus trying to create black holes. They're taking gold atoms and accelerating them in opposite directions in long tunnels. They accelerate them to a tiny fraction of the speed of light and collide them against each other. When they collide, temperatures of up to 20 trillion degrees centigrade are reached. These temperatures are thought to be hotter than anything we know of in the universe. It is believed that such temperature was only reached for a millionth of a second after the Big Bang. The underlying belief of this experiment is that if the two atoms collide at such a speed, a large amount of energy would be released in a very small space and a black hole might just get formed. We discovered that creating a black hole would take even more energy than that. More energy than any earthbound material could hold, at least according to Einstein's theory of gravity. Another theory suggests that there are more than 3 dimensions we've always thought there to be. This theory is key to another research project in Europe. If this theory proves true, we could be like insects living on water. The surface of our water would be our universe. We would only be aware of the 2 dimensions of the water and oblivious to the 3rd dimension of depth and the complex world underneath. Fish would be swimming underwater and causing disturbances which we could see and feel on the surface of the water, but we would not be able to find the cause. Similarly, we can see our universe changing around us, but cannot figure out why. The idea of this research project is that there are extra dimensions which intersect our world, but we just don't know about them. It is believed that when the particles collide at extremely high energies, the extra dimensions increase the gravitational forces between them enough to create a micro black hole. No such result has been reached yet. Scientists will know that a black hole has formed when they see the particles which had been predicted by Hawking's theory. If black holes are a ticking time bomb, then the end of the universe could be when the last black hole explodes. A rough estimate given till this happens is 1 Google years. A Google year is basically 1 followed by 100 zeros. If this is the case, a charge has been set on our universe and will go off when the last black hole explodes. Thanks for watching.